going to look at this video lecture in technical mathematics about the properties of inequalities. There are several videos that follow this area of lecture, and you can find most of those on the website. At any time, feel free to stop or pause or take a look at the material in more depth. Ready to get started? Inequality symbols. Now, you should be familiar with symbols like plus, minus, multiply by, and divided by. These symbols are for inequalities, meaning greater than, less than, greater than or equal to, and less than or equal to. In these forms of symbols, you find exactly what x is equal to. In these forms, x will be equal to a series of numbers. And that's what we're going to be working with. A little technical lingo first. These are referred to as the sides. Here's the inequality symbol. It happens to be less than, and these are the signs. Now this, you see two inequality. This is referred to as a compound. I didn't spell that right. Oh boy. Your spelling goes too when you do too much math. Compound inequality. Okay, there we go. Compound inequality. Now there are three types of inequalities to look at. A conditional inequality is true for some real numbers, but false for others. Let me give you an example. How about x is greater than or equal to 5? All right, if I use any number 5 and above, such as a 6, it's greater than 5. So it's true for any number 5 and above. But if I were to use 4, 4 is not greater than or equal to 5. So it's false for others. That would be a number 4. And this would be a 5 or a 6. So it's true for some numbers, but false for others. All right, here we go. How about an absolute inequality? That's what we like. We don't like these guessing games, right? Absolute inequality. True for all real numbers. Now, I have to put a little addition on here in order to make this come out. X plus 1 is greater than or equal to x. No matter what number I put in here, 1, 2, 3, 4, all real numbers. Whenever I add 1 to it, it's going to be greater than the original number. Always true for all real numbers. How about a contradictory inequality? False for all real numbers. Now what would that be? What if we took the same thing? X plus 1 is less than x. Okay, think about it again. If I put 2 in here, 2 plus 1 is 3. 3 is not less than 2. I put 4, 5, 6. Whenever I add 1 to it, it's not going to be less than the original number. So it's false for all real numbers. All right, we'll examine these three different types of inequalities. Let's first take a look at the boring part, the properties of inequalities, and these change a little bit from equalities. Okay, first, if A is less than B, then I can add anything to it and still it remain less. If I say A, we'll use these throughout. If I say A is 1 and B is 2, and we'll say C is 3. So I'd have 1 plus 3 and 2 plus 3. So that's 4 is less than 5. Yes, it's absolutely true. So what's that saying is I can add a number to both of these numbers and it still remains less than. All right? What if I multiply it by a number? What if I still take 1 and 2? And C has to be greater than 0, so it has to be a positive number. So we'll use that 3 again. Okay, 1 times 3 is less than 2 times 3. And 3 is less than 6. So as long as C is greater than 0, a positive number, the sign remains the same, less than. And the same in division. It stays less than. Now, the problem we have here is when C is less than 0. That would be a negative 3. And we'll use 1 and 2 again. Now, if we take 1 times a negative 3 and 2 times a negative 3, what do we have here? Negative 3 and negative 6, it's greater than. So whenever I multiply or divide by a negative number, less than 0, a negative number, I flip the sign. Starts out less than, and we have to change it to greater than. Okay, this one's the same thing. We can do our n as a c, or I think you can get the idea by now. If a is less than b, and we raise it to an exponent, or we put it in radical 4, nothing changes. It still remains less than. Here we have our absolute values. If a is greater than 0, so this is a positive number, 6. Okay, that means x will be between 6. Okay. Now, if a is greater than 0, I think I did that the wrong way. We're going to have negative 6, no, we're going to have 6 is greater than a, but we didn't get an out. Let's do 1. 6 is greater than 1. Okay, so we'll name a 1. That's greater than 0. 1. And we'll put in here, no, let's put in here negative 6. Right. It comes out as 6, right? So 6 is greater than 1, or 6 is less than negative 1. Negative 6 is less than negative 1. Okay, we'll see how these two work. I think they're going to make a little more sense when we put them in the problems. So let's take a look at doing some of our problems. 4x is greater than negative 8. Let's solve this problem. We divide by 4, and we get x is less than negative 2. So on our graph, we put 0, and we put negative 2, and we put an open circle because it doesn't have an equal sign. Then any number less than negative 2 is going to solve this problem. We tried negative 3. Yes, negative 12 is less than negative 8. So no matter what we use, as long as it's less than negative 2, it will solve this problem. Okay, here's another problem. Now what we need to do in this problem is combine like terms. So let's subtract 3 first. And I'm writing down the algebra. I know you have the skills, but 4 minus 3x is less than or equal to 5x. Okay, now we will add 3x and we'll get 4 is less than or equal to 8x, and x is less than or equal to 1/2. Let's graph that. And let's see, this time it's greater than or equal to. So we'll, and any of the numbers greater than or equal to 1/2 is going to solve that problem, right? If we used 1, 1/2 is less than 1, certainly does solve that. All right, I think we're going along just fine. Let's try this one. This is a fraction. Okay, the first thing we're going to do is multiply both sides by 3. And we'll get x plus 2 is greater than, we can simplify this 3 and 6, 5/2. Okay, so we subtract 2. Subtract 2, that would be subtracting 4/2. X is greater than 1/2. Let's draw our graph again. And it's greater than, so it's an open circle. And it's anything greater than 1/2. All right, here is an absolute value. Now, the symbol here is greater than. So whatever we have in here has to be greater than 6. So 3x plus 9 has to be less than or equal to negative 6. Okay. And our other equation is 3x plus 9 is greater than 6. These are the two extremes, negative 6 and 6. When it's greater than, it has two extremes. Let's plot this. Oh, we better figure it out first, right? Subtract 9. Okay, let's see, 3x, we subtract 9, should give us negative 3, and x should be greater than or equal to negative 1. Okay, now we've got something to plot. let's put -5 here. And we'll put -1 here. And we'll just put 0 here. Now, what do we have? X is less than or equal to -5. That's a solid dot because it can be equal to. Anything less than is this direction. X is greater than or equal to -1. That's a solid dot again. And it's anything greater. So you see what I'm saying is, when the symbol is greater than or equal to with an absolute value, it's the extremes. The extreme value and the extreme value on this side, the extremes. When it's less than, we'll find that it'll be within this section. Okay, here is a compound problem for us. And all we have to do is remove the inside. So let's see, should we take out the 5 first? Let's subtract 5. So we get -11 is less than -3x is less than or equal to 12. No problem there. But now is where things are going to change. See this negative number in here? And what we have to do is divide by -3, divide by -3 to get that to the outside. Now what happens when I told you we divide by a number less than 0, divide by a negative number? It flips the signs, right? So we have 11/3, and now we have greater than x and greater than or equal to -4. Now we can rewrite this a little bit to see, to put them in order. Okay, -4 is smaller than 11/3. So I'm just going to put that way down on the left side. Right? So now I have my smallest number and my largest number. And x is going to be in between these two numbers. That's how I read that, in between. Let's see what the graph looks like. Here's -4. Here's 0. Here's 11/3. You see why I changed it around now? It's a little bit easier to work with. Oh, I didn't change it around. I rewrote it and didn't change it around. Nope, that stays less than. And that stays less than or equal to. Oh boy, boy. Let's get this straightened out. I'm sorry. Let's get this straightened out. -4 is less than or equal to x, which is less than 11/3. That may be what I had up there. I'm not sure. Okay, so x is actually between -4 and 11/3. I think that's what I had. So it's a solid dot here. And it's an open dot here. And our answer is anything in between here. Okay? So it can't go greater than -4 or less than -4, and it can't go greater than 11/3. It has to be in between. I'm sorry about that. Okay, what do we have here? A word problem. A rectangular solar collector. All right, we can draw that. Oh boy. And it's L length, and it's 1.5 meters high. It didn't give us the length, but it will supply, in other words, the total is 600 watts per meter squared. And said the total is in between 2,400 and 4,000. Okay, let's just keep track of that. 2,400 is less than T is less than 4,000. All right, now we know that 1.5 meters times L meters equals 600. Okay, so 1.5 times 600, if we have L meters, and we divide that by 1.5, we end up with 900. All right, so let's put it in our equation. 2,400, and we should keep our units there, is less than 900 L is less than 4,000 watts. Okay, so if we divide the 900, we end up into 2.67, which didn't come out, meters is less than L is less than 4.44 meters. So this L, this length, can be anything in between 2.67 and 4.44 meters and still stay within this total wattage. All right? So we just used our inequalities for area, and then we used our two extremes that we were given in the problem. All right? This is the end of the lecture. Hope you enjoyed yourself and you'll listen to others. Thank you.